Hello and welcome to this Test 3 review for calculus. Our test is in just a couple of days, so hopefully this review is helpful. I'm just going to mostly work on this, commenting when I need to, which is for a lot of the problems, but not all of them. Okay, so let's just get started here. For question 1, we're just being asked to take a derivative of a kind of ugly function. Sorry, that was a mistake. Okay, so all that I did here, maybe I'll try to highlight some of this. When I took a derivative of this outside function, natural log, I got 1 over all of the other stuff. And then, when I took a derivative of the arcsine, I get 1 over the square root of 1 minus all of the stuff in the arcsine function squared. And then finally, this last piece here was just taking a derivative of this last inside function. Okay. For question 2, we're being asked to find the derivative of this function. So g prime of x, we're going to use the product rule. The derivative of the first term is 3x squared plus 2. We leave the second term alone. And then we leave the first term alone and take the derivative of the second term. So that second term, the derivative of ln is 1 over. And then we have to remember the derivative of tangent is secant squared. So there might be some other ways to rewrite that last piece, but I'm going to leave it like this for our sake. Okay. So the next question that we might have, or that we do have, is this one, which is about derivatives of inverse functions. So what I really want to remind you of here is the general rule that the derivative of an inverse at a point is 1 over the derivative of the original function at a different point. So this different point I'll call A. What's the relationship between A and B? H of A is the output B. So that's the one rule that's being tested here. So we're told that 12 equals the derivative of the inverse at 5. And by this rule, this has to equal 1 over the derivative of the original function at some other point. It may not be 5. It has to be some value that I'll call A. And so what's the relationship between A and 5? We know that h of A has to equal 5. So if I go look through the problem, what I find here is h of 2 equals 5. So that was telling me A equals 2. So I can go back to this problem and say, I've just learned that 12 equals 1 over h prime of 2. So if I rearrange this equation, I learn that h prime of 2 is 1 over 12. Okay, so for this question, question 4, it asks us just to compute the derivative of this weird-looking function, 5 to the arctangent x. So for this one, they're really asking about two properties, two derivative rules, I should say. Do we know how to take the derivative of exponential functions? So what's the derivative of 5 to something? It's 5 to that same something times a natural log of 5. And the chain rule says we have to multiply by the derivative of arctangent. So this really is asking, do you remember the derivative of these exponential functions? And do you remember the derivative of arctangent? So I'm going to write that natural log of 5 first. And it's times 5 to the arctangent. And then the derivative of arctangent is this lovely expression, 1 over 1 plus x squared. So that would be my final answer. Okay. Number 5 may seem like a slightly different question, but it's asked using this language of increasing and decreasing. And so I actually hear this as, really this is asking about the first derivative. So all the questions leading up to this point were asking about derivatives, and so is this one. It's just asking about these derivatives using these words, increasing and decreasing. Okay, so let's take a derivative. If f of x is 7 to the x, then f prime of x is just the natural log of 7 times 7 to the x. So here's the point. This is the natural log of 7 times a positive number. Why is 7 to the x positive? Because it's 7 to a power. There's no number you can put in for x that will make 7 to the x negative. And the natural log of 7 is also positive. Why is the natural log of 7 positive? Well, let me sketch a little graph of the natural log function. It's 0 at 1 and it's negative before 1. And it's positive after 1. So it's positive at 7. So we have that f prime is positive, which means that f is increasing everywhere from negative infinity to infinity. So that's our answer. It means that f is not decreasing anywhere. Okay. 6 says, for which values of a positive number a is the function log base a of x increasing? For which values is it decreasing? So you can actually answer this question without using any calculus. You might be able to answer it just remembering from some facts from your algebra course. But let's go ahead and use calculus for this. If f of x is the log base a of x, then f prime of x is 1 over the natural log of a times 1 over x. And one thing that's worth remembering here is that the domain of f, for any logarithm, it's just your positive numbers. So what this tells me is that the derivative, 1 over x, at least that part of the derivative, is also positive. So what we learn here is that the sign of f prime of x is completely determined by the sign of this thing, 1 over natural log a. So what we'll have is f prime will be positive if 1 over the natural log of a is positive, and f prime will be negative if 1 over the natural log of a is negative. Well, I'll stick to the part of the column I've created on the left. It's not too hard to see that if 1 over natural log of a is positive, that's the same thing as saying the natural log of a is positive. And now I can undo the natural log of a by e'ing both sides, and e to the 0 is 1. So f prime is positive whenever this number a is bigger than 1, so we're increasing if a is bigger than 1. Similarly, you can work out on this other side. The math works out exactly analogously. So the second derivative will be negative, the first derivative will be negative if a is less than 1. So we're decreasing if we have a less than 1. Those are our two answers for this question. Alright. So for number 7, we're asked to simplify this expression. It's the secant of the arctangent of 1 over x. And specifically, what we usually mean by simplify or rewrite is rewrite this so that there's no secants or tangents or arctangents or anything like that. There's no trig functions. Whenever you see a trig function and an inverse trig function that don't just cancel, so like an arctangent and a sine, or a cosine and an arcsine, something like that, what you want to do is think of right triangles. So I like to go and say, well, let's use the angle named theta for the inverse trig part. So if I rewrite this, this will tell me that tangent theta is 1 over x. Alright, this is really a pre-calc question. This question could have been asked in your pre-calc class. And tangent, when you're talking about a right triangle, refers to opposite over adjacent. So this tells us we can draw a right triangle, label one of the angles theta, and then the opposite I can make 1, the adjacent I can make x. By the Pythagorean theorem, the hypotenuse is 1 squared plus x squared, all in a square root. And so now from this picture, I can see that the secant of theta, and really that's the secant of what I said theta was, which is the arctangent of 1 over x. Well, that's just 1 over the cosine of theta. And in this picture, cosine is just adjacent over hypotenuse, so 1 over that is hypotenuse over adjacent. And so my hypotenuse is the square root of 1 plus x squared. My adjacent side is x. So here is a nice way to rewrite this bizarre function that doesn't use any trig expressions. Okay, so question 8 is asking about tangent lines. For tangent lines, we need a point and a slope. So we need an x1 comma y1, and we need a way to figure out the slope m. Well, we're told x1 is 0, so that's good. But y1 is the output of this function when we plug in x1 equals 0. So y1 will be 3 to the 0 plus 0 cubed, which is just 1. So now we just need the slope. And to get the slope, we're going to have to take a derivative, of course. So the derivative is, let's see, 3 to the x plus x cubed. Differentiated is natural log 3 times 3 to the x plus 3x squared. And now, when I plug in x equals 0, I get the natural log of 3 times 3 to the 0 plus 3 times 0, which is 0. So my slope is just the natural log of 3 times 1. So that's m. So now I have all three ingredients to build this tangent line. The tangent line should be y minus y1, so 1, equals the slope, natural log of 3, times x minus 0. You might slightly rewrite this as y minus 1 equals x times natural log 3. There's a bunch of ways to write this. So question 9 is a question about L'Hopital's rule, and it's really asking, does L'Hopital's rule apply to this limit? If it does apply, then we want to use it. So when I plug in x equals 1, I get the natural log of 1 minus 1 plus 1, all divided by the sine of pi times 1. Well, on top, that's a natural log of 1, and in the denominator I get 0. Thankfully, the natural log of 1 is 0. So when I try to plug in 1, I get 0 over 0. That is a form where L'Hopital's rule applies. So yes, it applies. That's part of my answer here. But now we want to actually use it. So this limit, according to L'Hopital's rule, I take a derivative of the numerator. That's 1 over x minus x squared plus x cubed. All of that times the derivative of that stuff in the ln. So that would be 1 minus 2x plus 3x squared, all divided by, and the derivative of sine is cosine, and the derivative of pi x is pi. And I just realized I didn't leave enough room here to write the limit. So L'Hopital's rule says this is the same as the limit as x goes to 1 of these two derivatives. And now maybe we can try plugging in x equals 1. When I plug in 1 to that numerator part, I get 1 over 1 into that first part, times when I plug into that second part of the numerator, I get 1 minus 2 plus 3, so I just get 2. And then when I plug in 1 into the denominator, I get pi times cosine of pi, which is negative pi. So when I rewrite that, that's negative 2 over pi. So the full answer to this question is yes, the rule applies to the limit, and the limit equals negative 2 over pi. Okay. So number 10 asks, does L'Hopital's rule apply to the following limit? If so, use it. If not, do it another way. So here we're going to try to plug in x equals infinity. And one thing that's important to remember is the arctangent of infinity does go to a number, that's pi over 2. And 2 to the negative infinity, we can interpret that as 0. So the first thing to realize is that when I try to plug in this limit, x going to infinity, I don't get 0 over 0. I don't get infinity over infinity. I don't get infinity times 0. And I don't get infinity minus infinity. I get none of my L'Hopital forms. So the first thing I can note right away is L'Hopital's rule does not apply. So if I'm going to conclude anything about this limit, it's not because of L'Hopital's rule. But the next thing I can notice is that by virtue of having tried to plug in x equals infinity, this non-L'Hopital's form already told me what the limit was. the numerator is pi over 2, that's a non-zero number. Whenever you get a non-zero number divided by 0, this also tells you that the limit does not exist. So we kind of learned two things at once. It happened that L'Hopital's rule didn't apply, and what showed us L'Hopital's rule didn't apply already answered the limit question. Okay, so number 11 asks us to think about the limit as x goes to 0 from the right of x times natural log x. If you plug in 0, you get 0 times the natural log of 0 is negative infinity. And this is a form that L'Hopital's rule can handle. So part of our answer is yes, the rule applies. That's definitely part of our answer to this question. And now we just need to actually apply it. So by L'Hopital's rule, this limit equals the limit. Oh wait, I'm not gonna use L'Hopital's rule just yet. First I need to rewrite this. So I have the limit as x goes to 0 from the right of x times the natural log of x. And I'm going to rewrite this as x going to 0 from the right of the natural log of x divided by 1 over x. And so if I wanted to test this at this stage, I could try to plug in 0. I would get negative infinity over infinity, and now I can just use L'Hopital's rule directly. So I'll take a derivative of the top guy, which is 1 over x, divided by taking derivative of the bottom guy, negative 1 over x squared. And now hopefully I can just rewrite this limit a whole bunch. I'll get negative x squared over x, and that simplifies a little bit more into negative x. So of course I can plug in, I get that this limit is just 0. So the limit is 0, and yes, the rule applied. I don't know why this equal sign got a little mark on it. Okay. The next question is a little more different or abstract looking. It asks us, for which values of a does L'Hopital's rule apply to this following limit? And find the limit for these values. So if you look at this limiting expression, x is going to this number a, and part of the expression depends on a. So this may seem like a very different type of problem, but really, if you know how to use L'Hopital's rule, even though this seems different, you can totally get this problem. The first thing to note is that the numerator has a limit no matter what a is. So as x goes to the number a, if we just plug that in, we get 1 minus e to the 0, which is 1 minus 1, which is 0. So the numerator, no matter what a is, the numerator is always going to 0. But the denominator doesn't always go to 0. It goes to a squared minus 4. So this fraction, if we plug in x equals a, is always going to 0 divided by a squared minus 4. Once we make that observation, the rest of the problem sort of spills out. Because for L'Hopital's rule to apply, we need infinity over infinity, or infinity times 0, or infinity minus infinity, or 0 over 0. Well, we know we have a 0 in the numerator, so we need the denominator to be 0 also, so that we can apply L'Hopital's rule. So for this question, we need this to equal 0, so we need this part to equal 0, which tells us a has to be 2, or a can be negative 2. So there are two values for a where L'Hopital's rule applies. Okay, so I'm going to use L'Hopital's rule for either value of a. So I'm going to use L'Hopital's rule, assuming a is one of these numbers. And when I use L'Hopital's rule, I get the limit as x goes to a. The derivative of the top is just negative e to the x minus a. And the derivative of the denominator is 2x. When I plug in a, I get negative e to the a minus a, all divided by 2a. Well, that numerator is negative e to the 0, and e to the 0 is 1. So what does this tell me? I know that when a equals 2, L'Hopital's rule applies, and the limit is negative 1 over 2 times 2. That's negative 1 over 4. When a equals negative 2, L'Hopital's rule applies, and the limit is negative 1 over 2 times negative 2, and you'll get positive 1/4 for that limit. Okay, so for number 13, we're asked to find the critical numbers of this function, and critical numbers are where the derivative is 0 or the derivative does not exist at points in the domain. So in either event, we're going to have to take a derivative, and so the derivative of this function requires us to know the derivative of arcsine. So that's the square root of 1 minus all that stuff squared times the derivative of x squared plus x, so 2x plus 1. So it's true that this expression won't exist, this derivative won't exist, if that stuff in the square root is 0. But the only way to make that stuff in the square root 0 is to make, oh gosh, I can't see that, I'm sorry. The only way to make that stuff in the square root 0 is to make this stuff that I've highlighted 0. Or sorry, make that stuff that I've highlighted equal to 1 or negative 1. But if that blue stuff equals 1 or negative 1, then this stuff equals 1 or negative 1 in the original function. And if you think about the arcsine function, its domain is all inputs between negative 1 and 1. So those places where that blue stuff is 1 or negative 1, the derivative's not going to exist, but that's okay. We're not going to call those critical numbers per se, because they're at the ends, the endpoints of the domain. The critical numbers we really want to care about come from this part of the derivative being 0. So that's what I'm going to focus on. 2x plus 1 will equal 0, and that'll cause x to have to equal negative 1/2. So I do want to say that x equals negative 1/2 is really the critical number we're looking for. I just want to make sure it's in the domain of this weird function. So to check that, I'm going to do negative 1/2 squared plus 1/2, and just make sure that this is between 1 and negative 1. But this is 1/4 plus 1/2, which is 3/4, and that is in the domain. That's in the domain of inverse sine. So this x value is in the domain of our function. So that's our critical number. Alright, number 14 asks us to use differentials to approximate a square root of a weird number. And the way to use differentials is to kind of think of our derivative definition. F of x plus h is pretty much f of x plus f prime of x all times h. So once we remember this kind of formula, it's up to us to choose what x and x plus h are. The way I like to think about it is x needs to be something I can plug into my function and its derivative without having to use some annoying calculator. So what's a number close to 98.6 that I can take the square root of? And of course I'm thinking of 100. And so then I need x plus h to equal this weird number. So what I need is h, if I work that out, is negative 1.4. And if you really think about what's going on, f of x is our square root function. So we're sort of naming all the parts so that we can estimate this weird square root. Then f prime of x, I just take a derivative of my square root function, I get this expression. So f of 100 is just the square root of 100, that's 10. F prime of 100, that's 1 over 2 times the square root of 100. I'll just get 20. And then h is negative 1.4. So I'm going to plug all those pieces in to the stuff I wrote on the left. F is the square root function. X plus h is 98.6. This is approximately f of x, we said was 10, plus f prime of x, we said was 1 over 20, times 1.4. So you would probably use a very basic calculator to finish computing that to get a good approximation. Okay, for 15, it's a question that talks about concavity. And concavity is all about a second derivative. So we're just looking for where is the second derivative, positive or negative. Fortunately, the first derivative of this function works out to be quite nice. F prime is 1 times log base 2 of x plus x times the derivative of log base 2, which is 1 over natural log of 2 times 1 over x. But if you think about it, that x and that 1 over x cancel. And so I just get that the derivative is log base 2 of x plus 1 over this weird number, natural log 2. So when I take a second derivative, I take a derivative of log base 2 of x, that's 1 over natural log of 2 times 1 over x. And then that extra constant, 1 over natural log 2, differentiated to 0. So the last thing to consider about this question is what's the sign of 1 over x, and what's the sign of 1 over natural log 2? Well, 1 over natural log 2, that's 1 over a positive number, so that's positive. And 1 over x, I claim, is also positive, because the domain for our original function had x being positive. So 1 over x is positive. So this is positive. So this tells us that we're concave up. Alright. Question 16 seems a little weird, or at least it does to me, but it turns out not to be so bad. So let me read carefully what it says. It says, consider a function, g of x, which is the log base a of x plus the log base b of x. And a and b are, of course, positive numbers, and neither one is 1. If we are told that g of x has a critical number at x equals a, then what is the value of g of a? Well, this is a different sounding kind of question, but I promise if it's showing up on a calculus test or assignment, you have to be able to use calculus to do it. So the first thing we might want to do is just try and plug in g of a, even though we don't even know what the number a is. G of a would be the log base a of a plus the log base b of a. And so g of a, one thing we can say is the log base a of a is 1. And the log base b of a, well, maybe I don't know what that is. So that's about all I can say right now. But notice, so far, I haven't used that we have a critical number when x equals a. Critical numbers are when the derivative is 0 or undefined. So let's take a derivative. G prime of x. The derivative of log base a of x, that's 1 over natural log of a times 1 over x, plus the derivative of log base b is 1 over natural log of b times 1 over x. And so what do I learn here? I know that g prime of a, I'm going to have a 1 over a times a 1 over natural log of a, and a 1 over a times a 1 over natural log of b. So I just factored that 1 over a out. And so now I get to say, is this expression, it's got to be where the derivative is 0 or undefined, but if you look at this expression, a is just some positive number, so there's no way this expression is undefined. In order for this to be a critical number, this has to be 0. And in order for this whole expression to be 0, this thing in parentheses that I'm highlighting in orange has to equal 0. So all that stuff in orange, I have to have that 1 over natural log a plus 1 over natural log b is 0. So if I write that down, I'll get 1 over natural log a plus 1 over natural log b is 0. If I work that out a little bit, I'll get 1 over natural log a equals negative 1 over natural log b. If I apply 1 over to both sides, I learn that natural log of a equals negative natural log of b. And here's where I'm going to use another sneaky fact about logarithms. That negative 1 out front, I can write as the natural log of b to the negative 1 power. That's the natural log of 1 over b. So that now if I do e to both sides, I learn something. A had to equal 1 over b. And so I'm going to highlight this in a different color. I'm going to go back, maybe highlight it in green. A equals 1 over b, which means I can plug that in right over here when I plugged in g of a. So when I plug that in for g of a, I get that g of a equals 1 plus log base b of 1 over b. And now I can use some last familiar facts about logarithms. The log base b of 1 over b is negative 1. So I'll write over here, what did I learn about g of a? G of a was 1 plus negative 1. G of a had to be 0. So just to walk through this question, I had to use the fact that when I plug in a, I have the derivative is 0. That told me what I highlighted in green. Then I plugged in a to my original function, and I replaced a with 1 over b, and part of that to learn that g of a is 1 plus negative 1. Okay, just 2 more questions. See if I have enough room here. 17 says, suppose f of x is differentiable and its domain is all real numbers, and suppose its derivative is negative. Is it true or false that this new function, g of x, defined to be e to the f of x, is decreasing? Well, a calculus way of answering this is to just take a derivative of g of x. And you know how to use chain rule here. The derivative of e is just e, and then I'm going to multiply by the derivative of that inside function. And so the thing to recall here is right here that I'm highlighting in red, this part of the derivative, it's e to a number. So this is always positive. E to any number is positive. And so we have that the derivative for g is a positive number times f prime of x. And we were told f prime of x is a negative number. But a positive number times a negative number is always negative. So what did we learn? G prime of x is always negative, and that tells us g is decreasing. So this was a true statement. Okay, I think we're finally back at our last one, number 18. It says, if we are told that a function f of 2 equals 3, and the derivative f prime of 2 equals negative 1, then can we find the equation for the line tangent to the graph of the inverse at the point 3, 2? So I'm going to focus on tangent to the graph of this at the point 3, 2. I'm going to focus on that for a second. I'm going to say, oh, we need a y minus y1 equals m times x minus x1. And so here I'm using x1 is 3 and y1 is 2, which is another way of saying that f inverse of 3, because that's the function we're making a tangent line for, equals the output 2. And this equation I just wrote is another way of saying that 3 equals f of 2. And we were told that in the problem, so this all checks out. So the thing we need here really is the number m. And m is the derivative of the function f inverse at x1, so at 3. But again, using our rule about inverses, we know that this is 1 over the derivative of the original function, not at 3, but at a point, maybe I'll call it a, related to 3. We know we want f of a to equal 3. Well, if you go look to where I put that red check mark over here, we know what we plug into f to get 3. A has to equal 2. So this has to equal 1 over f prime of 2. And f prime of 2 is negative 1. And 1 divided by negative 1 is negative 1. So now I found m. I have y1, I have x1. So I can write my tangent line as y minus 2 equals negative 1 times x minus 3. That's a perfectly good way to write your tangent line. You can also write it like this. Both of these are excellent ways. Okay. I hope everything is going well for you guys. I hope that review kind of helps. Good luck on your exams. Good luck with everything going on in your classes and your lives. I hope to hear from you soon. Goodbye.